our identification subsystem, our main task was to do sensor layout and algorithm design. To do that, we first made more detailed environment specifications and design requirements. For our design, we chose to combine LiDAR distance measurements with computer vision from a camera. The LiDAR would give us more robust detection of harvestable asparagus, and the computer vision allows us to have more accurate position information for each asparagus. The computer vision is broken down into 3 stages: a segmentation, object detection, and position estimation stage. And as a demonstration of feasibility, we implemented the first two stages. So here we see an input image, we do segmentation, and then the object detection stage. And we have yet to implement a final filtering step, so some noisy objects are also detected.
All right, so now we're going to be discussing the navigation subsystem updates. So the navigation system will obviously, again, just be a simple line following algorithm. We're going to have a blue strap on the ground, blue because it's the direct opposite of brown. And the AsparaBot will be traversing the row, keeping its sensor over the blue line, and we'll know if it deviates off the blue line that it's gone over the dirt, and we'll bring it back. So some specs, obviously briefly, it's got to be resistant to the elements, especially UV radiation, water, and rot. And of the 3 materials that are listed below, we found that polypropylene is the one that's going to be the most resistant, specifically UV, water, and rot. It actually works out very nicely. And now in terms of sensors, we're just going to have a very simple IR LED and photodiode. Photodiode is going to be picking up how much of that light is reflected off of. So we're going to do a test case, multiple test cases. We'll test what it should be and what it shouldn't be by projecting it over dirt, for example, and we'll set that as the baseline and allow some leeway in case we need to. That's it. Thank you.
For the UI system, we decided on something like this: simple screen and buttons. Robustness was important in the decision making since we will be working with a lot of dirt, so nothing too complicated. And also this gives us the basics for a simple operation by the customer.
Hi guys, so a quick update on the chassis subsystem. So our main goal for at this time was to make 3 to 5 sketches and kind of weigh each one and think about the pros and cons, and then decide on a final sketch. So on the bottom are the 3 sketches, and on the top is kind of how each sketch was weighed against each other. The first one is the one on the top left. It was supposed to be foldable, and that way it could be more easily stored. The one on the bottom is sort of the same thing, but with a tarp over it. And the one on the right is kind of like a boxed version, so it's more rigid. And the third one is actually what we ended up deciding with. And this isn't for specifically this week's update, but it's kind of our progress as of right now. We're trying to put together a preliminary CAD. The dimensions might need to be more fleshed out and flexible, but right now this is what our assembly looks like. Thank you.
For our gantry design, we've kind of decided on using a belt-driven y-axis and a lead screw-driven z-axis. So where y-axis refers to the side-to-side motion and z-axis is up and down. We're also planning on implementing some x-axis translation, but for the purposes of our prototype and for this week, we haven't really explored that in too much detail. So here's the preliminary CAD that we had for the demo. Some design features are that we have that belt-driven y-axis and non-captive lead screw z-axis. We're using slotted aluminum extrusions for support and traversal. Some future things that we're planning on doing are adding some more protection for the exposed belts and lead screws, because we plan to be in a pretty dusty environment and we foresee some maintenance issues with that.
Okay, so for material selection, the main materials we're going to use for the gantry are aluminum, rubber, and PETG. And they're all going to be used for different components. For a breakdown of why we chose those materials, you can go to the link below. It has a little bit more detail on that.
This week, the actuator is working on design selection. So on the left, you can see one design with 2 motors, and the top component, which is the gripper, has 1 fixed claw and the other side is rotating. And on the right side, you can see a single motor, where the gripper has two rotating sides, but the motion of the gripper closing is coupled with the motion of the cutter swinging. And the factors that we evaluated these designs on in order of descending importance were torque capacity to cut the asparagus, the system volume, so the size of the actual assembly, which has to fit in between the asparagus density that we've specified, the robustness of the mechanisms, as well as the cost to manufacture. And based on these, we decided that the dual motor design would be optimal for our solution.